They asked me once, what keeps me awake at night? Not the bomb, not the fire I brought down from the heavens. No, what haunts me is far more subtle. It's the question of what lies beneath. Beneath matter, beneath space, beneath everything we think we know. I spent my life spitting atoms, watching them break apart like fragile shells. But even then, I knew we were only scratching the surface. Every answer revealed 10 more questions. Every particle we discovered hinted at something deeper, something hidden. Now, decades after my time, they've built something extraordinary. A machine so vast, so powerful, it makes our work at Los Alamos look like child's play. They call it CERN, the Large Hadron Collider, a 17-mile ring buried beneath the Earth, where protons race at nearly the speed of light before smashing into each other with unimaginable force. And what they've found there, it changes everything. You see, we thought we understood reality. We thought matter was solid, predictable, bound by laws we could write on a chalkboard. But CERN has shown us something different, something that suggests our reality isn't quite as real as we believed. Let me take you back to the beginning, to the question that started it all. What is everything made of? The ancient Greeks wondered this. They imagined tiny, indivisible particles they called atoms. They thought if you could keep cutting matter in half, eventually you'd reach something that couldn't be cut anymore, the fundamental building block. They were wrong, but they were also closer to the truth than they realized. When I was young, we knew atoms weren't indivisible. We'd already discovered electrons orbiting a nucleus. Inside that nucleus, protons and neutrons packed together like passengers in a crowded train. We thought that was the end of the story. But then we started colliding particles at higher energies, and we found something strange. Protons and neutrons weren't fundamental either. They were made of smaller things, quarks, bound together by particles called gluons, held in place by forces so strong they could never be separated. We called it the Standard Model, a beautiful mathematical framework that described every particle, every force, except gravity. Electrons, quarks, photons, carrying light, gluons, binding matter together, the W and Z bosons responsible for radioactive decay. And for years it worked perfectly, but there was a problem, a missing piece. All these particles had mass, weight, but according to our equations, they shouldn't. The mathematics demanded they be massless, zipping through space at light speed like photons. Obviously, that wasn't true. Matter has mass. You have mass. I have mass. So where did it come from? In the 1960s, a physicist named Peter Higgs proposed something radical. He suggested there was a field permeating all of space, invisible, unavoidable. Every particle we know moves through this field constantly. And as they move through it, they interact with it. They slow down. They gain resistance. That resistance, that's what we call mass. Think of it like walking through water. In air, you move freely, but step into a pool, and suddenly every movement requires effort. The water resists you. The deeper you go, the harder it becomes. The Higgs field works the same way. Particles moving through it gain mass depending on how strongly they interact with it. Electrons interact slightly, they have little mass. Quarks interact more strongly, they have more mass. Photons don't interact at all. They remain massless, traveling at light speed forever. It was elegant, beautiful. But was it real? For 50 years we didn't know. The Higgs field was just mathematics, a theory, untested, unproven. Until CERN turned on the Large Hadron Collider, they accelerated protons to 99.999% the speed of light. At that speed, time itself slows down for those protons. They experience only a fraction of a second while years pass outside, then they collided them. The energy released was staggering. For a brief instant, conditions inside that collision chamber matched the universe moments after the Big Bang. Temperatures reached 5 trillion degrees. Space itself boiled with energy. And in that chaos, something appeared, a particle that shouldn't exist, a particle so massive, so unstable, it decayed in less than a trillionth of a second. But its signature was unmistakable. The Higgs boson, the particle that creates the Higgs field, the particle responsible for giving everything mass, they'd found it, proven it. Reality itself was confirmed. But that discovery opened a door to something far stranger. Because once you confirm the Higgs field exists, you have to confront what it means. It means that space isn't empty. It never was. Even in the darkest void, far from stars and galaxies, the Higgs field exists, filling everything, permeating everything. You're moving through it right now. Every atom in your body is interacting with it. Your mass, your weight, your very existence depends on this invisible ocean we're swimming through. But here's where it gets disturbing. The Higgs field has a value, a strength, and that value determines how particles gain mass. Change that value even slightly, and everything changes. If the Higgs field were stronger, particles would have more mass, atoms would be heavier, chemistry would be different, stars might never form, life as we know it couldn't exist. If it were weaker, particles would have less mass, matter would barely interact, the universe would be a cold, empty void of massless particles racing through darkness. The value we observe is perfect, precisely calibrated, almost impossibly so. And that's the problem, because according to quantum mechanics, fields don't just sit at one value. They fluctuate, they bubble, they exist in multiple states at once until measured. The Higgs field should be unstable, constantly shifting. But it's not. It's locked at exactly the value needed for our universe to exist. Why? Some physicists suggest we're just lucky, that in an infinite universe, some regions have the right value, and we happen to live in one of them. Anthropic principle, they call it. We observe this value because if it were different, we wouldn't be here to observe anything. I never liked that answer. It feels like giving up. Others suggest something more unsettling. What if the Higgs field isn't stable? What if it only appears stable because we're observing it from inside this particular state? Imagine a ball sitting in a valley. It looks stable. It's been there for billions of years. But what if that valley isn't the lowest point? What if there's a deeper valley nearby, separated by a hill? The ball is stable until something gives it enough energy to roll over that hill. Then it falls into the lower valley, the true ground state. Physicists call this vacuum decay, and if it happens to the Higgs field, reality as we know it ends. Not slowly, not gradually, instantaneously. At some random point in space, the Higgs field would quantum tunnel to its true lowest energy state. A bubble of new physics would form, expanding outward at the speed of light. Inside that bubble, the Higgs field has a different value. Particles have different masses, atoms can't form, chemistry doesn't work. Everything the bubble touches is annihilated, not destroyed, exactly, transformed, rewritten at the fundamental level. And there's no warning, no defense. You wouldn't see it coming because it travels at light speed. The wall of changed reality would hit you in the same instant you could possibly see it approach. One moment you exist, the next, the universe has moved on without you. CERN's calculations are concerning. They've measured the mass of the Higgs boson, they've measured the mass of the top quark, and when you plug those numbers into the equations, something troubling emerges. our universe appears to be metastable. Not fully stable, not completely unstable, balanced on a knife's edge. The current state of the Higgs field is like that ball in the valley. It's stable for now, but it's not in the deepest possible valley. The true vacuum lies somewhere else. How long do we have? Billions of years, probably, maybe trillions. The probability of vacuum decay is incredibly small across the timescale of a human life, across the timescale of civilizations, even across the timescale of stars. But eventually, given enough time, it's not a matter of if, it's a matter of when, unless we're missing something. This is where CERN's recent discoveries become truly strange. In their particle collisions, they've observed anomalies, tiny discrepancies between what the standard model predicts and what actually happens. Muons, which are like heavy electrons, wobble slightly more than they should when moving through magnetic fields. The decay rate of certain particles doesn't quite match predictions. New particles might be appearing in the data, particles we never expected. These could be experimental errors, flukes, statistical noise, or they could be evidence of something beyond the standard model. Additional fields, additional particles, hidden dimensions. You see, our reality might have more than 3 spatial dimensions. We experience length, width, and height, but string theory suggests there could be 6 or 7 more dimensions curled up so small we never noticed them. At everyday scales, these extra dimensions are irrelevant, but at the quantum level, inside CERN's particle collisions, they might matter. Particles might be leaking into these extra dimensions. Energy might be disappearing from our reality into somewhere else. And if that's happening, what's coming back? There are theories, controversial theories, that suggest the Higgs field might be connected to these extra dimensions, that it might be a bridge between our reality and something beyond. When CERN creates Higgs bosons, they're not just creating particles, they're momentarily opening doorways, tiny, brief, lasting less than a trillionth of a second. But doorways nonetheless. To where? Some physicists speculate about parallel universes, other bubble universes with different laws of physics, born from the same quantum foam that created ours. Maybe the Higgs field extends beyond our universe. Maybe it connects to others. If that's true, then what CERN is doing is unprecedented. They're not just studying our reality. They're touching the boundary of it. And boundaries, in my experience, are dangerous places. I remember standing in the New Mexico desert, watching the first atomic bomb explode. In that moment, we released energy that had been locked in matter for billions of years. We broke a seal that nature had placed there. Some of my colleagues worried we might ignite the atmosphere, that the temperatures and pressures could trigger runaway fusion in the nitrogen and oxygen around us, turning Earth into a brief new star. The calculations said it was impossible, probably impossible, almost certainly impossible. We detonated it anyway. The atmosphere didn't ignite. We were right, that time. But the principle remains. When you push physics to its limits, you're gambling. You're betting that your mathematics is complete, that you haven't missed something crucial. CERN is pushing further than we ever did. They're recreating conditions that haven't existed since the first moments of the universe. They're probing energies where space and time themselves become uncertain, where particles and forces blur together. And they're finding things they didn't expect. Microscopic black holes might be forming in those collisions, lasting only an instant before evaporating in a burst of Hawking radiation. If extra dimensions exist, the energy threshold for creating black holes drops dramatically. What seems impossible in 3 dimensions becomes routine in 10. These black holes are harmless, too small, too brief. They evaporate before they can consume even a single atom, probably. But what if one doesn't? What if under just the right conditions, a black hole stabilizes, starts growing. It would sink to the center of the Earth, consuming matter as it goes. Slowly at first, then faster. Within years, decades at most, Earth would collapse into a black hole the size of a marble. CERN safety assessments say this is impossible. The cosmic rays hitting Earth constantly carry far more energy than the LHC produces. If such black holes were dangerous, Earth would have been consumed long ago. It's a good argument, a convincing argument. But it assumes we understand all the variables. What if the act of creating black holes artificially is different from natural formation? What if the conditions inside a particle accelerator with its precisely controlled beams and magnetic fields allow for something cosmic rays can't achieve? What if we're wrong? I'm not saying we are. I'm saying the question haunts me, because the deeper CERN digs, the more questions emerge. They've found evidence that suggests matter and antimatter might not be perfect opposites, that the universe treats them slightly differently. This asymmetry is why matter won after the Big Bang, why anything exists at all rather than everything annihilating into pure energy. But we don't know why this asymmetry exists. The standard model doesn't explain it. There must be new physics, hidden rules, forces we haven't discovered. And if there are hidden forces, what else is hidden? Some physicists propose that dark matter, the invisible substance that makes up most of the universe's mass, might be detectable at CERN. It might be particles that barely interact with normal matter, passing through us constantly without a trace, except at high energies, in violent collisions, where they might briefly appear. If CERN detects dark matter particles, it changes everything. It means we're not alone in the universe. Not in the sense of aliens, but in the sense that our reality is a small subset of a much larger cosmos, that most of existence is invisible to us, perceivable only through gravity. We'd be like fish in the ocean, suddenly realizing the ocean is just a small part of a vast world above the water, a world we never imagined. But the most unsettling possibility is this. What if consciousness itself is connected to quantum mechanics, to the act of observation collapsing wave functions? At CERN, they're observing particles in states that shouldn't exist, particles existing in superposition, being in multiple places simultaneously until measured. The act of measurement forces them to choose, to become real. But what is measurement? What makes an observation count? When does the wave function collapse? When the particle hits a detector, when the detector sends a signal to a computer, when a scientist looks at the data? Where does the quantum world end and the classical world begin? We don't know. And if consciousness plays a role, if awareness itself affects quantum outcomes, then what is CERN really doing? They're not just observing particles, they're observing the fundamental building blocks of reality, the deepest layers of existence. Are they discovering what's there, or are they creating it through the act of looking? It sounds like philosophy, but quantum mechanics blurs the line between philosophy and physics. The universe, at its deepest level, is probabilistic, not deterministic. Things don't have defined values until measured. Particles exist in clouds of possibility, becoming concrete only when observed. If that's true at the particle level, could it be true at larger scales? Could reality itself be probabilistic, becoming definite only when observed? And if so, what happens when CERN observes something that was never meant to be seen? I don't have answers. I only have questions, but I know this. Every time we've pushed the boundaries of knowledge, we've discovered that reality is stranger than we imagined. The atom wasn't indivisible. Space and time aren't absolute. Matter and energy are interchangeable. Each revelation overturned centuries of certainty. CERN is pushing further than anyone has before, into energy regimes where our theories grow uncertain, where mathematics gives multiple answers and we don't know which is real. They're shining a light into the darkness, and something might be looking back. I spent my life becoming death, the destroyer of worlds. I harnessed the power of the sun and turned it into a weapon. But what CERN is doing is different. They're not destroying, they're revealing, peeling back the layers of reality, exposing the machinery beneath. And I wonder, late at night, whether some things are meant to remain hidden, not because they're dangerous, but because knowing them changes us, changes what we are, changes what reality is. The Higgs field gives us mass, makes us real, solid, concrete. But underneath it all, we're just ripples in quantum fields, probabilities that collapsed into existence, sustained by forces we barely understand. CERN is showing us that truth, forcing us to confront it. We're not as real as we thought, and that might be the most disturbing revelation of all. The experiment continues. The collisions keep happening. Every second, millions of protons smash together at nearly light speed, tearing open the fabric of space-time, revealing glimpses of something beyond. What will they find next? A new particle? A new force? Evidence of extra dimensions? Or something we can't even imagine yet? Something that doesn't fit our categories? Something that breaks the rules we thought were unbreakable? I won't live to see it. My time has passed. But you will, and when that moment comes, when CERN announces they've found something that changes everything, remember this: we asked for this. We built the machine. We collided the particles. We opened the door. And whatever comes through, we'll have to face it. That's the burden of knowledge. That's the price of seeing beyond.